restate. So we can ask the question in the following way. We can say, like, imagine that I give you a vector, even not just non-zero integers. You can ask that like just non-zero reals, and you take a uniformly chosen vector in the Boolean hypercube, and we can define the atom probability of A to be the maximal atom, right? Like we define it as rho of A is just the maximum over all R's, all reals of the probability that fx equals R, where x is a random plus minus one vector. And then the Littlewood Offord problem is just like to find some upper bound. They asked for some upper bound on rho star, which is the maximum atom probability over all non-zero. When I say non-zero vector, I mean non-zero in every coordinate in R to the n. And such a result is referred to as an anti-concentration inequality, as opposed to concentration inequalities when we want to show that something like that random variable is very well concentrated around its mean. Here we want to show that actually the probability to hit any specific number is not that large. Some simple examples are the following. You can think about the vector A to be a constant vector. Let's say that all the coordinates are 1. For simplicity, let's assume that n is even. It doesn't change the answer much or at all. Then in this scenario, it's clear that the atom probability of this vector A is exactly n choose n over 2 times 2 to the minus n, just because, like, you know, like the maximal probability attains when you want to hit the number 0, and then you need to have exactly n over 2 plus 1s and exactly n over 2 minus 1s. Okay, and n choose n over 2 times 2 to the minus n is roughly like some constant over square root of n. The constant here is not important, but the expression will be a little bit important later. Another example, we can take a dyadic sequence, just all powers of 2, 2 to the 0, 2 to the 1, 2 squared, etc., etc. And we know in such a sequence that each number is at most one representation as a signed sum of the AIs. And therefore, if this is our vector A, so its atom probability is exactly 2 to the minus n, because we cannot represent the same number in two ways. And some intermediate example, which is also quite important, and with some history, is the example if you take A to be all the numbers between 1 to n, 1, 2, 3, 4, up to n. In this scenario, we can do some heuristic calculation, but actually to prove it precisely, it's a little bit more complicated, but not super hard. So just heuristically, we can think about the variance of the linear function. So the variance is just the sum of the components of the coefficient square, which is around theta of n cubed. And therefore, we expect that everything will be concentrated in plus minus 1 standard deviation, which is n to the 1.5. And if we believe in the heuristic argument that in this plus minus standard deviation, we have more or less a uniform distribution, then we expect the atom probability to be n to the minus 1.5. Clearly, what I said now is not a mathematical statement, but it's actually true that this is the answer. The atom probability is n to the minus 1.5. Any questions so far? No. And so we can ask the following question: why is it even interesting, this kind of problem? So many people can answer many, can give many answers to this question. So for me, in terms of combinatorial geometry perspective, we are studying the intersection of a hyperplane with a discrete hypercube, which I think is quite interesting. In terms of the additive combinatorics, we are studying the sums of subsets of a given set of numbers, right? So this is the main theme in additive combinatorics. More perspectives, it is a very important tool in the study of random polynomials and random matrices, like the Littlewood Offord theory. And also, at least I'm interested in, and okay, many people are interested in, but like I will tell you a little bit later, like what is the exact problem that I'm interested in, maybe. But nonlinear generalization and graph, hypergraph statistics, and more. So the first question that we should ask is how can we approach such a problem? And so perhaps the most naive thing to do is just to try to apply the central limit theorem. So the central limit theorem asserts that if we have sum of IIDs, it converges to a normal distribution. And this indeed gives us a non-trivial answer to the Littlewood Offord problem in case that all the AIs are the same. And a more quantitative version of the central limit theorem, which is the Berry-Essens theorem, shows that also gives us a non-trivial answer, also in case where the AIs are not exactly the same, but they cannot differ too much from each other. But already in 1943, Littlewood and Offord, when they asked the question, they gave an almost optimal answer. And they showed that the atom probability is at most log n over square root of n without any assumption on the AIs, just that all of them are non-zero.
Asaf, there is some noise, some echo noise, as if you have an echo to what you're saying. I don't know if it is from your equipment or something else.
Oh, maybe. Let's see. Let me just turn off my mic for a second. Is it now better or not?
Yes, now it seems to be good. Okay, thanks.
Okay. Thank you. So Littlewood and Offord, they showed like an almost optimal, they gave an almost optimal answer. When I say optimal, again, we can interpret the word optimal in many ways here, and we'll talk about it a little bit more. And shortly after, Erdős came with a beautiful proof, and he showed that the atom probability is at most n choose n over 2 times 2 to the minus n. Okay, and this is tight because we can take A to be the all one vector, and we've already seen that this is the answer for this vector. And just in case that there is even one person in the audience that is not familiar with this proof, I want to talk about this proof because it's super short and neat, and it's something that I think it's must have in your pocket. So before that, one remark is that this is a really general statement that all without any assumption on the vector A, right? So we saw that if, like, even in cases where CLT and the Berry-Essens do not apply, that the AIs are very far from each other or whatever, it gives us the answer, and we don't have any assumption except of the fact that all the coefficients are non-zero. And in fact, if you can allow some zero coefficients, but just like the zeros are redundant. So if you have some zero coefficients, just ignore them, and instead of n in this solution, just write the size of the support of A. And if I want to talk about the proof a little bit, so let me define something. A family of subsets of n is called the Sperner family if and only if there are no two sets in the family for which one of them contains the other. Okay, so this is called the Sperner family. Or in other words, it's an anti-chain if you take the partial ordering of inclusion of sets. So for example, if you take the sets of the collection of all subsets of the same size, the numbers 1 to n, so clearly it's a Sperner family. If you want to optimize it, so it sounds like intuitively that the worst case scenario that you can do, like the largest Sperner family that you can choose is of size n choose n over 2. And indeed, Sperner's theorem from 1928 asserts that every Sperner family is of size at most n choose n over 2. Now, having Sperner's theorem in hand, we can present the proof of Erdős for the atom probability. So just let me recall the setting. So we have a vector AIs, right? A1 up to AN. All of them are non-zero. So first reduction, right? Because we are looking at a linear combination of them, sum of AI xi, where all the xi are plus minus 1 independently at random. So first assumption that we can assume that all the AIs are positive because it doesn't change the probability, right? Because we have a signed sum and everything is uniform. So let's assume that all the AIs are positive and fix some target number, some target real that we want to hit, right? And we want to upper bound what's the probability to hit this number. And now we can let this fancy A be the collection of all subsets A of coordinates, let's say all the positions of ones in solutions of fx equals r. Okay, so we have sum of AIs where I is in A minus sum of AJ where J is in A complement. So you just look at the set of all solutions. Maybe there are no solutions, and then like the atom probability for this specific R, like it's 0. And if we look at the set of all solutions, I just want to show you that this set cannot be that large. So since AI is larger than 0, if you think about it for 1 second, you will see that this set mathcal A is a Sperner family. Okay? So think about it for a second. And because it's a Sperner family, it means that it's of size at most n choose n over 2. And the probability for each such solution is 2 to the minus n. So we know that there are at most n choose n over 2 times 2 to the minus n many solutions. And this completes the proof. Any questions?
Yes, somewhere near the beginning, you mentioned something about the A's being integers. I gather that that's not really an aspect of this problem.
No, it's not an aspect. Yeah, it's not an aspect of this problem. This was the original problem, but like that's it. We changed it.
And there's no particular, nothing happens when the A's become integers. The problem doesn't change. The results don't change, right?
Right. I think that maybe the integers that I wrote at the beginning is even a typo. It wasn't the original problem. It's just like for me, like when I will start talking about random matrices, I will talk only about integers. So that's why I wrote integers, probably by mistake, but it doesn't change anything here. Okay, it's a good point, right? So this proof, in this proof, we didn't use the fact that the AIs are integer. They can be any non-zero number. So after seeing like Erdős proof, and I told you that it's an optimal result, so we can ask, is it the end or just the beginning? Because if it's an optimal result, what else can we do? So there are a few other possible directions to keep exploring this problem. For example, we can assume more structure, make some structural assumptions on A, and then ask, how does the atom probability change? And indeed, there is a lot of work on it. The classical results about it are due to Erdős and Moser, Sarkozy and Zemeredi and Stanley. For example, they show that if the AIs are distinct, then the atom probability is at most n to the minus 1.5. And actually, Stanley showed something which is, in my opinion, it's super nice. It's a nice proof also that the sequence 1 to n is actually the extremal sequence, right? It gives the worst case atom probability in case that they are all distinct. And more results in these directions were obtained by Halas, by Nguyen, Tao, and Fu, and we will discuss it later. And another kind of problem that we can ask, okay, so this was one thing, like assuming more structure, we can ask for inverse problems. Suppose that the atom probability is large, what can we say about A, right? Like the more structure, we do the other way around. We say, let's assume that A has more and more structure, or has less and less structure. What can we say about the atom probability? Here we can do the opposite, ask if the atom probability is large, what can we say about the structure of A? We can also ask the same question for higher dimensions. And we can also ask robustness kind of problems that I will start with robustness, but I will try to cover all these aspects. So let's start with the robustness, which is a problem that it's something like a little bit older that I did a few years ago, but is related, is the following. Suppose that we look at this problem. Okay, so we have this function f, the linear function, and we can ask how robust is the property that f is not equal something, right? We saw that the probability, that the atom probability, if we take A to be a vector such that all the coefficients are non-zero, so the atom probability is little O of 1, right? I don't even care what is the precise thing. Erdős said that it's at most like constant over square root of n, but let's just start with little O of 1. We know that it's little O of 1. And the question is how robust this property. So more formally, suppose that we fix some vector in plus minus 1 to the n and r, and we can define a parameter to say like rrx is the minimum number of coordinates we must flip in x to make f equals r. Okay? So if you think about it, like I give you an x, and we can look at the set of all the solutions to f equals r in the Boolean hypercube. And now for every element, for every vertex in the hypercube, I can ask what is the Hamming distance from a solution. Okay? And then we can ask, the main problem that we were concerned with is what is the typical behavior of this parameter in the worst case scenario. That is, which k do we have that for every a and r, at least 1 minus epsilon proportion of vectors satisfy that the distance of the vector from a solution to f equals r is larger than k. Or equivalently, we can ask what is the largest K, such that if we consider the set of all solutions to F equals R, we look at all the solution in the Boolean hypercube, and then we take the Hamming ball around the solution with radius K. So you want to see what is the maximal K, such that this Hamming ball is still quite small.
You're assuming that there are solutions, yes? I mean, there's something.
Yes, of course. I always assume that there is a solution. Okay. Like I want the worst case scenario. There is no solution, so you just like it, right? So there are no solutions at all. You can do whatever you want, and you cannot eat the solution. Okay, that's why I said in the problem, I said that in the worst case, because again, if there are no solutions, just that the problem is not interesting, because then I can tell you just change whatever you want, you can never eat the solution. Okay, so let me try to emphasize the problem here, just to make sure that you're on the same page. Okay, we'll see it in the next slide. Just let's try to understand what's going on here. So we know by the proof of Erdős, we know that the set of all solutions form a kind of a Sperner family, right? Like if we look at the set of ones, like you take the set of all solutions in every vector in the hypercube, which is a solution to this linear equation, you look just the subset of the ones coordinates, then we know that it's a Sperner family. And in order to get an upper bound, we are looking for a Sperner family that expands quickly in the hypercube, right? That's what we want to try to understand, what's going on. A natural guess to see how this parameter behaves is just to take a large Sperner family. Let's say you just take the middle layer and choose n/2. And if we take the middle layer and we want to look at the Hamming distance, at the Hamming ball around the middle layer, so if we want to take a radius such that this Hamming ball of this radius will capture like at least epsilon proportion, so we see that we need to take radius of around square root of n. So this is a decent guess that if we just take a Sperner family, we need radius of roughly square root of n in order to cover like some positive proportion of the Boolean hypercube. But an old theorem of Fourier, Decaan, and Kleitman, they showed that there is a Sperner family with a one shadow. Don't think about one shadow. Just think about Hamming distance one. Okay, which is not exactly one shadow, but they showed that there is a Sperner family such that even if you look at the Hamming ball with radius 1, right, you're allowed to change only one entry from each of them, then it already captures a positive proportion of the Boolean hypercube. So it means that the theta of square root of n is no longer a decent guess, and maybe a decent guess now is just to say that we are allowed to change only like one or constant many entries. So that's what I said here, that at first glance, if you look at this theorem, it seems like the above gives like a guess that this parameter R, by the way, I call R for resilience or robustness. It gives that the robustness should be 1 for some R and the vector A. If not, then we can conclude that these arithmetic Sperner families, right? Because like it's not really a Sperner family. The Sperner family that Fourier, Decaan, and Kleitman showed, it's like, let's call it a real Sperner family. But in this case, like the Sperner families that are coming from solution to these linear equations are very arithmetic in some sense, right? Because it's a solution for some linear equation. It's not that for every Sperner family, we can assign some equation, some linear equation that this Sperner family is the set of solutions. So this will give us another evidence that these arithmetic Sperner families are structurally special. So let's try to understand the bounds. So clearly by the Erdős-Littlewood Offord inequality, we know that this robustness is larger than 0, because if you give me some target R, the probability to hit R is little of 1, right? So I need to do something. I need to make some changes in order to have a solution. And also it's not hard to show that this parameter is larger than 1, that actually you need to change more than one entry. Because indeed, suppose that A has D distinct entries. So in particular, if we have D distinct entries, one should avoid eating D numbers, right? Because if you eat one of these D entries, so by one modification, I can make, let's say, the vector 0. But what do we know from this Erdős-Moser? We know that the atom probability, if we have d distinct entries, is of the form like d to the minus 1.5. And then we can just take a union bound and see that if you change only one entry, so with high probability, you will not be able to eat, let's say, the number 0 or any other number. And let's try to understand what's going on with an upper bound. For example, if we take the vector, which is all ones, right? And I ask you, for example, to eat 0. So clearly you need to change roughly square root of n many entries, right? Because we know that typically a typical answer, like if you just take a typical signed sum, it will be like around like theta of square root of n. But we can do much, much, much better. For example, if you take the vector A to be like almost all the coordinates are 1, and the last log n coordinates is just a dyadic sequence, all the powers of 2, like 1, 2, 4, 8, 16, all the way to n. So with such a vector, like deterministically, we know that if you want to eat 0, I can do at most log n changes. And basically with the last log n coordinates, I can cancel out almost everything that I want. Okay. And a theorem of me together with Afonso Bandera, which is now in ETH, and Matthew Korn, which is now in Stanford and soon will move to IST, we show that for every A, typically an adversary cannot make f being 0 by flipping at most log to the base 3 of log n signs. And quite surprisingly, we also have an example that there exists an A such that an adversary can typically make it 0 by flipping log to the base 3 log n many signs. So we managed to really like solve it like quite tightly. And we saw that the kind of the threshold here is like log to the base 3 of log n. And the lower bound is based on structural partitioning argument combined with the Berry-Yassine theorem. And for the upper bound is interesting by its own. It's based on some explicit construction of what we call an economic additive base. And I remind you that what is an additive basis? An additive basis is just, so this is the definition, an order H additive basis of n is a set S such that every number between 1 and n can be represented as a sum of at most H elements of S. And when I say the word economic, I mean that the sum of squares is very small, right? Because we want something that can cancel out every number that we can get, that we can typically get, but cannot cause problems. So we just want the variance to be quite small. Examples for additive bases, for example, you can take all the odd integers or order 2 bases because every number can be represented as a sum of at most 2 odd integers. A little bit less trivial additive base is this set of squares. This is a theorem of Lagrange that every number again can be represented by as a sum of at most 4 squares. And the idea in the proof was to include an additive basis of small order in A, and then we used it to cancel out the rest of the sequence. And I'm not going to talk about the proof. Any questions so far? No? Okay. So let's move on to the second part. The second part about this anti-concentration, we can talk about anti-concentration in higher dimensions. And the motivating examples, at least for me as a combinatorialist, that's why I started working on thinking about anti-concentration in higher dimensions, was the following. Okay, it's still not the question, just let's start with some notation. So an order n Hadamard matrix, I hope that everyone knows what is it, but even if not, so it's an n by n matrix with entries plus minus 1, whose rows are pairwise orthogonal. Okay, just an orthogonal matrix with all the entries plus minus 1s. And let Hn be the number of such matrices of order n. It is not hard to see that Hn is actually 0 for every n which is not divisible by 4. Actually, this is quite simple if you just consider the first 3 rows of a Hadamard matrix, right? We can change signs of complete like columns or rows if we want, and it's still a Hadamard matrix. So we can always assume without loss of generality that the very first row is all ones. And then clearly the second row, because it must be orthogonal to the first, must have exactly n over 2 plus ones and n over 2 minus ones. And then you can go to the third row and you can convince yourself that n must be divisible by 4. And actually, this is a major conjecture, like, is it even true that 4n is enough? Meaning that if you take that for every n which is divisible by 4, there is a Hadamard matrix of order n. And I think that the best known bound for it is, actually, I'm not sure if someone broke it or not, is like what they call the devil's number, right? I think that 666 is the threshold, like that the minute you find with computers, all the Hadamard matrices up to 666, and then you can ask me, okay, 666 is not divisible by 4, so it's, I think, 664, I think, is the largest number that okay, it's not the largest number that people manage to find Hadamard matrix, because Hadamard matrices exist for every, for example, power of 2. There are many special cases, but if we just look at all the numbers divisible by 4, so I think people manage to cover
the
everything.
smallest unknown case of the conjecture.
The smallest unknown case of the conjecture, right? So is it the 664 or no? Or you didn't? Oh, yes, thank you. But the question that I was interested at, I said, okay, it's very hard to find Hadamard matrices, but let's try to understand like the structure and hopefully maybe it will give me ideas how to construct them. And so the question that we ask is, how large can Hn be? Instead of showing that it's non-zero, I just wanted to show that it's not very large, like regardless. And now let's try to get some intuition. So it's not very hard to show that the number of Hadamard matrices of order n Hadamard matrices is at most this ugly product. Okay, why? Because how many options do we have for the first row? We have 2 to the n many options because it's a plus minus 1 vector. And then if we restrict ourselves to the Boolean hypercube, so now you want the number of vectors in the Boolean hypercube is just orthogonal to the first row, and this we know that we have at most 2 to the n minus 1, and then you want the number of vectors in the Boolean hypercube that are orthogonal to the first 2, etc., etc. So it's just a product of 2 to the n minus k, which is roughly 2 to the n square over 2 plus little of n square. Or this product exactly is just 2 to the n choose 2. Okay, so this is a trivial upper bound for the number of Hadamard matrices. And just to compare, the number of n by n plus minus 1 matrices is 2 to the n square. So it already shows why Hadamard matrices are very hard, are very rare, right? Because it captures like only a square root of the number of total, at most like square root of the total number of plus minus 1 matrices. But we actually wanted to try to do better. And so I'm not sure that I stated the conjecture in the slides. I will see in the next one that we actually guess that the number of Hadamard matrices, even if they exist, it should be 2 to the little of n square. But it wasn't such an easy task even to break this trivial bound. So as the first thing to do, we just wanted to try to do something slightly better than 2 to the n square over 2. And I say slightly better, it's better in the exponent, right? Not 2 to the n square over 2 divided by 5%. Okay? And let's try to understand this problem and how is it even related to this anti-concentration in higher dimension. So imagine that we want to construct a Hadamard matrix 1 row at a time. And at time step k plus 1, we need to add a new row, which satisfies the following system of linear equations. You have this current matrix HK, which is a k by n plus minus 1 matrix, where the k rows are orthogonal. And now you want to multiply them by a vector rk plus 1 of length n. So this gives us a form of the following, like a term of the following form, like sum of ai xi, where the ai's are the column vectors. Now these are vectors and not numbers. And the xi's are plus minus 1 variables. And you want to solve sum of ai xi equals 0. And this looks like a kind of an anti-concentration inequality. And we, of course, we are interested in the anti-concentration inequalities for these vectors. And clearly, if we can show that there are not too many such solutions, so we can start iterating and say that there are not too many Hadamard matrices. Okay, any question? No? So, yep.
This wasn't considered before?
No. Very surprisingly, it wasn't considered before. And this is one of my favorite problems. I'm not going to brag now. We just did a tiny improvement. Like I really want to try to show the 2 to the little orphan square. Okay. So I just want to show the connection in our small contribution, but like, I think the most interesting question is just to show that it's 2 to the little orphan square. And I think that it's a very natural question to consider. And I also think that it's true. And also it gives another evidence why Hadamard matrices are so hard. So the first thing to try, like at least when we started thinking about this problem, and in a moment I will say who is we, so we just Googled, we said, okay, for sure there is some anti-concentration inequalities for vectors, let's just apply them. So the main tool was this theorem due to Halas. It says that if you have a collection of vectors in R to the D, and suppose that there exists some M, blah, blah, you know, don't even read all the details here. Let's just look at the display. So the atom probability, right, of this sum, of this signed sum, is at most whatever, some constant that depends on D. I remind you, D is the dimension. In my example, D was K, okay? And so the 1 over square root of M to the D is good, even though that we still don't know what is this M, because you don't need to read it now. But the problem is with this constant that depends on the dimension. So the constant in Halas inequality is D raised to the D, okay? Is like D to the D. And this means that there is no chance for us to iterate this anti-concentration inequality in the Hadamard setting all the way to something linear, right? Because if I scroll back with this strategy, when I want to iterate and every time add one row at a time, if I really want to gain something large in the form, like to get even like not 2 to the n square over 2, like to get 2 to the 1/2 minus epsilon times n square. So I really want a bound that I can iterate linearly many times. Okay, so the main problem here was that this constant that depends on the dimension is actually D to the D. So we cannot iterate it more than, I think, like roughly square root of n many times. Okay, so this is the explanation that even if we take M to be n, which is the number of vectors, which clearly is the best that we can do, so this inequality is useless if D is larger than square root of n. So what we did together with Vishesh Jain and with Yufei Zhao, we showed that if you have a collection of vectors in R to the D, and we have some condition, the condition is quite robust. We said that just imagine that we have like many vectors, which are relatively short. When I say relatively short, you have like n vectors, and the vectors are of length of dimension, let's say epsilon, and for some small epsilon. So you have many vectors which are short, okay, and they have some robust property. What is the robust property? Is that like you want to partition them, you want to be able to partition them to sets, not necessarily square matrices, to sets such that each set has a relatively large rank. Here I didn't say relatively large, I just wrote everything in terms of ranks. But like the idea is that just imagine that I have like n vectors that I can really partition to some constant many sets, such that let's say that each of them is full rank or almost full rank. So what we showed that the atom probability is of the form 2 to the minus L, L choose L over 2 raised to the average rank. So if all the ranks, let's say, are full, so you see that you have something here raised to the rank, okay? So you get exponential raised to the rank, and 2 to the minus L times L choose L over 2, this is clearly smaller than 1 for every L. So we have some bound that we can actually use all the way to like linearly many steps in the at least in the Hadamard procedure exposure. And what is also nice here is that this inequality is tight, right? Just think about a matrix, a K by N matrix, which is just a collection of K by K identity matrices. So this is exactly what you get, because 2 to the minus L, L choose L over 2, this is just what you get in each coordinate from the Littlewood Offord inequality. Okay, and I hope that from this kind of theorem, it's clear how to get like at least some improvement for Adamard. Unfortunately, the improvement wasn't that impressive. It was just like a 1 minus epsilon. And did I write it? Yes, okay. So clearly with not too much extra work, this gives us like the number of Adamard matrices is at most 2 to the 1/2 minus some constant times n square. Our constant, we can make it explicit. I think in our paper, we didn't bother to write it explicit. We can write, I don't know, 1/400. But I think that the more interesting problem is not to see the small improvement, just to try to prove that the number of Adamard matrices is 2 to the Littlewood Offord square. Any questions?
So what parameters, what is the add that you take in the proof of your theorem?
So the proof is not automatically, right? Because like, what do you want to do? So the idea is the following. All I want to show is that when I start exposing a Hadamard matrix, I don't even need to expose all the way to the end. I want to show that at some point, there is a linear length interval such that in each of them, in each of these exposure, I gain, right? So if I can show something like that, I'm done. So what do we want to do? We want to show that after you expose, let's say, the first epsilon n many rows, so there are two scenarios. Either we are now in a situation that we can apply this anti-concentration bound, meaning that we can partition the columns into relatively many subsets, right? You want L to be large, but it cannot be larger than constant. So either we are in a scenario that we can partition the columns into relatively many subsets, such that each of them has almost full rank, or it's just like a very atypical, it's a very atypical choice of rows, meaning that you already gained on the first epsilon n many rows. If you cannot partition them, it means that just there are not too many such matrices, right? Because if you think in terms of random matrices, we do expect that every large enough subset will be of almost full rank. And it just doesn't make sense that you cannot have you cannot have so many subsets with full rank, okay? So this is the not much extra work. It's not immediately from the anti-concentration bound, but really from this, it's just an exercise. And this conjecture I want to highlight, at least as a combinatorially, this is one of my favorite, but currently I have zero ideas how to get the 2 to the Littlewood Offord square. I do have ideas how to improve this 1/2 minus c to 1/4, but I don't see how to get to Littlewood Offord square. So, by the way, I forgot to ask, how much time do I have?
Usually 50 minutes and then 10 minutes for questions. So you have 10 more minutes from now.
Okay, perfect. This will be enough. So now let me move to the third part, which is inverse Littlewood Offord theory and counting. So far we asked for upper bounds on the atom probability in worst case examples. And now we want to understand the structure of vectors if you tell me that the atom probability is not too small. Right? For example, I think that it should be a relatively simple exercise to show that if the atom probability is exactly n choose n over 2 times 2 to the minus n, then it's a relatively simple exercise to show that it means that the AIs are all the same, that it's a constant vector, it's proportional to the all one vector. And so the inverse Littlewood Offord problem.
I think it's the equality case in Sperner, what you just said.
What, sorry?
It's the equality case of Sperner, I think, what you just said.
Right. And so the inverse Littlewood Offord problem raised by Tao and Fu in 2009 was that suppose that the atom probability is large, what can we say about A? And using deep Feynman type results from additive combinatorics, Tao and Fu, they showed that essentially the only reason for A to have atom probability, which is at least something polynomial, is that A is being contained in a generalized arithmetic progression. Okay, so that's what they showed. And just for some motivation, so in addition to the obvious mathematical beauty of this statement that to ask like how does A look like if we know that the atom probability is large? So one motivating reason to develop this theory, at least for Tao and Wu, was to tackle the following problem. which is the singularity problem for random matrices that we'll talk about. Like yesterday, there was some breakthrough, like last night in archive. Suppose that Mn is an n by n plus minus 1 matrix sampled from some probability distribution. See that there are many models for it. And the problem is just to compute what's the probability that Mn is single. Okay, so I give you some, let's say some plus minus 1 random matrix, some distribution, and we'll mention a few of them. And you want to try to estimate what's the probability to be singular. And there is much work on this problem, and we will mention it like, let's say later, but very soon. But first, let's try to understand how can we relate it to this inverse Littlewood Offord theory. And the idea is quite simple. So imagine that we can expose the first n minus 1 rows of the matrix, and that we expose the, okay, not in every model we can say, let's expose the first n minus 1 rows of the matrix, because then maybe you already lost all the randomness. But let's imagine that we can expose the n minus 1 rows of the matrix, and suppose that the rank of the exposed matrix is exactly n minus 1. So imagine that you have an n by n matrix. I give you the first n minus 1 rows of the matrix, and I also give you a present that tell you, okay, you don't need to check. The rank is n minus 1. Now, what will you do with the last row? So condition on the above. So we know that the first n minus 1 rows of the matrix, they span a vector space of dimension n minus 1. So it has a unique, up to scaling, a unique normal. So we can fix this vector in the orthogonal complement, and we can just ask what's the probability. And now you see, like if we condition on the above, so the probability to be singular is just the probability that the inner product between the new row, the nth row, and the null vector A is 0. Okay, and if we are lucky, and the atom probability of A of this null vector is small, then we are done. Okay, so this is all. So we can somehow like focus only on atom probability. So what is the main problem here is to try to exclude vectors that don't have a small atom probability from being in the null space. Okay, and now suppose that the above quantity is large. Right? So if the atom probability is large, so the inverse theorems says that the vector A, if the atom probability is large, then the vectors A with such atom probability are arithmetically structured. And therefore, at least in an intuitive level, so we know that there are not too many such vectors. So we hope just to be able to exclude them with a simple union. Okay. For example, if the atom probability is rho, and I'm telling you that, so what does it mean? That the probability for such a vector to be in the null space, it's like rho to the n. So if I'm telling you that there are much less than 1 over rho to the n many such vectors, so clearly I can exclude all of them. Okay, so everything here is about counting, and at least for this motivation, we don't care about the actual structure like we care about the counting parameter. We care how many such vectors are there, and we want to try to exclude them. And also in their survey, Hoy, Guyen, and Van Wu, they wrote that in most of the applications in random matrices, we don't use the inverse theorems directly, but we just use the counting corollaries. And so for us as combinatorialists, like if it's all about counting, so we want to count, but we want to have some discrete model. So as a first reduction to discretize the problem, we switch to finite fields, okay? And the problem that we are interested in is the following: how many vectors we have in ZQ to the n, where Q is some prime, and with a large atom probability. And as our starting point, just for the application, so our starting point was the following simple observation, that the probability for a random matrix, a plus minus 1 random matrix, to be singular over R is upper bounded by the probability that Mn is singular over ZQ. Okay? So if we can show that the probability to be singular over ZQ is small, so we also know that the probability to be singular over R is small.
So just to make sure, we're doing the arithmetic of the field of order Q, or just the entries come from ZQ?
No, so the entries are plus minus 1, right? In the okay, standard models that we are interested at. Okay.
So you really mean the field of order Q, right?
Yes. Okay, and I want to do just to calculate to do the singularity problem mod Q, right? Which is like somehow it looks like too much because you can lose it. It sounds too lossy, but so that's what I'm trying to explain here is that even though that it sounds too lossy, and indeed it's lossy if Q is small, right? But if I can show that even mod some Q, this probability is small, so clearly it implies the same thing over the rings. And the inverse Littlewood Offord theorems or finite field variants of Nguyen and Wood, for example, they give sharp counting results if by large atom probability we say like polynomial, okay? But in application, we also need to handle much smaller values of atom probability. And the goal is to get to exponential. And the restriction for polynomial comes from various exponential type losses from applying additive combinatorics machineries type as Feynman's theorem, etc. But for counting, we don't need Feynman's theorem because we don't care about the precise counting. We just care about the number of such vectors. And in order to count bad vectors, what we want to do, we want to be able to find some combinatorial condition on these vectors A that guarantee to have a large atom probability. And we don't have much time, so let me just speed up. So luckily such a condition exists. So there is a theorem of Halas, which I stated the Halas theorem for anti-concentration for vectors, but also there's anti-concentration for this linear equation, which is called Halas inequality, which is at least I think also by now as a general inequality, I think it's the best, the strongest concentration inequality. And in Halas inequality, there is some very combinatorial condition. So let's just make this definition. It's not the same R from the robustness part that I talked about. So given a vector in ZQ to the n and some k, which is at least 1, so we can define RKA to be the number of solutions to plus minus AI1 plus minus blah, 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 plus minus AI2k equals 0. Okay, you fix some k, and then you want to look at all the signed solutions to 0 when you can take repeated indices from the vector A. Right, so if you think about, you can think about it as there is some kind of some hypergraph hidden here. So we have this parameter RKA. If you're given an A, so theoretically you can just, and K, you can count how many such solutions exist. So you have this parameter RKA. And let me skip to understand the condition. Halas inequality asserts that the atom probability of A is upper bounded by some expression which depends on this RKA. Okay, so if we know the number of such solutions, so we can upper bound the atom probability by something depends on this RKA. So this is Halas inequality. So if we have this bound, so now it's natural to ask, okay, so how many vectors we have with RKA which is not that large, right, or with which is large, right? Okay, you can try to play with this parameter. So the intuition is just consider the set of all possible solutions. So you have a kind of a hypergraph on the vertex at ZQ. And now if you take a vector with large atom probability, so in some sense, it corresponds to a dense induced hypergraph. Okay? And then together with Vishesh Jan and with Kai Lu and with our own Wojtek, so we prove that for all T and K, the number of vectors in ZQ to the n with large RKA. And when I wrote large, you see this ugly expression, but forget about the T for a second. What is written inside, this is just the expected number, the expected size of RK. So we show that the number of vectors which have at least T times expectation, RKA, is at most, and we have a good counting expression. So we have Qn to the 2 times T to the minus n. Forget about this little of n, even though that it causes many problems, right? But we have the Q to the n times T to the minus n. And this gives us a relatively good counting result to tackle many the singularity problems for many studied models of random matrices. So for example, here, know that if RKA is T times the expectation, then the atom probability is at most T over Q times square root of n. And therefore, the probability that such a vector survive as a null vector is at most q to the n times t to the minus n times this rho raised to the n. But again, it's a small cheat here because I'm using the fact that all the rows are independent and there are models where the rows are not independent. But in theory, if we have such an expression, so now we can just take a union band and we can exclude all the bad vectors. And just to summarize, what does it give me? So the applications, for example, if I look at the independent model, so suppose that Mn is a random plus minus one matrix where all the entries are independent. The intuition says like that the atom, okay, clearly the singularity problem is at least 2 to the minus n, because if we consider two rows being the same, the probability is 2 to the minus n. And there is a long history for this specific problem, but quite impressively and quite recently, it was solved by Tihomirov in 2019. He showed that actually 2 to the minus n is the correct answer. Asymptotically, show that the upper bound is also like 1/2 plus little of 1 raised to the n. With our method, we cannot get anything exponential, but at least we get like a kind of an exercise, like one-page proof. You can show a bound of 2 to the minus n to the 1/3. Okay, in a very short and elementary proof. For the symmetric model, imagine that you take n by n plus minus 1 symmetric matrices. So this was also conjectured that the answer should be 2 to the minus n. But even to show that the probability is little of 1 was quite hard, right? It was settled in 2005 by Costello, Tau, and Wu, and they showed that the probability is upper bounded by n to the minus 1/8. Then Hoy-Guyen showed that the probability is like n to the minus little omega of 1, like it's smaller than any polynomial. Roman Vershinin showed in 2014 that the probability is like of exponential type with some unspecified small constant. And using this kind of counting argument together with Vishesh-Jan, we show that the probability is 2 to the minus n to the 1/4. And later, this was improved by Campos, Matos, Morris, and Morrison to 2 to the minus square root of n based on our technique. And I thought that this is the end of the story. But last night, not based on our technique, based on Tihomirov's technique, so Campos, Matos, Michelin, Jensen, and Julian, sorry, I don't know how to pronounce his last name, they showed that actually the singularity problem is exponential for symmetric matrices quite impressively. So that's what I did most of yesterday. I just tried to read and understand the paper, 48 pages. And there are more questions of this type. So a question of Van Wu, for example, is suppose that this is also one of my favorite questions, which is still like very open. Suppose that we are taking m random, so suppose that we are taking m random vectors in plus minus 1 to the n. How many signs can an adversary typically flip without being able to create dependencies? Okay, so Van Wu explicitly asked it for m equals n. So if you try to write explicitly, just imagine that you have an n by n plus minus 1 matrix, everything is independent. And the question is how many signs, so we know that with high probability, this matrix is non-singular. And the question is how many sign flips can we allow an adversary to make without being able to make dependencies? And the guess is that the answer should be roughly n/2. And you can also ask the question, like there's even a toy problem, which is super open, like, and that I have no idea how to tackle. Imagine that you take a plus minus 1 vector matrix, and I allow an adversary only to flip signs along the main diagonal. Can you show that with high probability, it cannot form dependencies, right? If an adversary flips the signs along the main diagonal. And the other question is, imagine that I allow an adversary to flip signs, but I upper bound the number of signs that the adversary can flip in each row and column, okay? So what is the largest case such that we can allow adversary to flip at most k signs in each row and column? And together with Kai Lu and Gwyneth McKinley, we show that if you take slightly less than n vectors, right? If you take an m by n matrix where m is slightly less than n, then typically an adversary needs to flip around like n/2 many signs, okay? But we have no idea how to get closer to it if you really take n by n matrix. And there are more models that we we tackled. So with Vishesh and Kyle and Wojtek, we did like exponential type bounds we got for models with 0-1 matrix where every row sums to D, where D is theta of n, and for signed adjacency matrix of randomly regular graphs. And quite recently, we saw, like together with Matthew Kwan and Lisa Sauerman, we showed that we showed a little of one bound, but based on these kind of techniques for 0-1 matrices, where every row sums to D, and D is at least 1 plus epsilon log n over n. So this solved the conjecture of Yuri Person and Elad Horeb. And we also tackled now, so we will upload to archive probably in the next week, a non-singularity for the adjacency matrix of the K-core of a random graph. This is joint work with Matthew Kwan and with Ashwin Shah and Mehtab Sonmi from MIT and more. And that's it.
Thank you very much. Thank you, Asaf, for the very nice talk. Are there any comments or questions?
Asaf, the Hadamard problem, what is the best known lower bound for the number of Hadamard matrices, say of order 2 to the k?
Yeah, so I never managed to come up with a lower bound which is better than 2 to the n. Again, ignore the trivial n factorial, right? You want like non-isomorphic Hadamard matrices, but let's say that you allow yourself also isomorphic Hadamard matrices, so I don't know how to do anything better than n to the n.
So it's between
like
2
for
to the n
non-isomorphic,
2 to the n squared times 49.
1/2 minus epsilon, yes. Yes.
About this, in my work with Greg Cooperberg and Shachar Lovet on this probabilistic method for showing existence of regular combinatorial structures, we mentioned at the end, I think, so it was Greg, I think, that did some simulations, and he thought that maybe there is e to the n log n Hadamard matrices of order n, and maybe of order 4 times n. And I just mentioned regarding this that our method does not apply to Hadamard matrices, but it applies to other designs. So this is a specific design, and then it gives you an exact formula for the number, even asymptotic, not just in the exponent, but in the prefactor for the number of designs of a certain size. You can use it for partial Hadamard matrices. So instead of n by n, you can do square root n by n or something, I don't know, some power, maybe eventually to square root. So you can use it to I don't know, the first rows to understand how many.
Can you do it for linearly many rows?
No.
I see.
But maybe square root. So I think maybe the way it's written, it's not even square root. I'm not sure. Maybe it's only n to the 1 over 100 times n. So n to the 1 over 100 rows, maybe. But maybe with these ideas you can go to square root n, maybe not.
I see, but square root of n still doesn't give you any improvement in the exponent.
No,
right?
probably not. I imagine not. But I'm just saying something can be counted precisely.
I see.
So okay. Questions of some type, some rigidity structures that can be counted exactly. And
I see.
You can try to extrapolate the formula, but probably the extrapolation would not be correct in the range you want.
I see. I will take a look at it. Thank you.
Sure.
Thank you very much, Asaf, and thank you all for listening. We'll
thank you.
Send announcements for the next meeting.
Thanks, Asaf.
Okay, thank you. Bye-bye.